So to finish off the semester, we're going to spend some time talking about statistics. Statistics is almost like a second language. So what we need to start off with is some vocabulary. First piece of vocabulary we want to talk about is something called a population. It might be a long day spelling today, by the way, we're starting off here. A population is nothing more than a group you want to learn about. Now, a group could be people, it could be medications, could be items. For you guys, it's mostly going to be parts produced. When you're talking about quality control, obviously that's the group you want to learn about, is the parts that you're trying to hold to a certain standard. In many cases, that population is not as easy to define as you would think. For example, let's say you wanted to answer the question, let's say there's a school board election coming up soon, and you want to know who's going to win, or you want to kind of predict who's going to win. That would be something that would be a good use of statistics, or a valid use of statistics. I don't know how good it would be. Well, what's your population there? Any ideas? Well, a lot of people would say, well, what I want to learn about is the candidates. Is that really what's going to determine the outcome of that election? Now, what you wanted to know, you wanted to predict who's going to win that election. So really what your population would be is the voters. So if you're looking at a school board election, your population is the voters. Now, not just all, a lot of people say, well, all registered voters. Well, not necessarily. You only care about voters who will vote in that election. Most school board elections get like a 25 to 30% turnout, by the way. So you only care about those who are going to vote, because the ones who stay home that day aren't going to affect the result of that election a whole lot. So now when we do one of these studies, what we're asking is a question. So for that school board example, the question would be, who would you vote for? For whom would you vote, however you want to do it. And probably more specifically, you would have to say something like, if the elections were held today, who would you be casting your vote for? Because if it's a month and a half or so away, they can't for sure predict who they're going to vote for. There may be things that happen to change that. The answer to that question is called the random variable. We'll come back and talk about that in a little bit. But anyway, a parameter is an answer to that question that describes the population. So again, let's say that you find that after the election, you count the votes and 57% of voters voted for candidate A. That would be a parameter because that describes the whole population. Attempting to gather information from the whole population is called a census. Every 10 years, our government attempts to do a census. We got one coming up here in about a year and a half, 2020. They've never actually done a true census because they have never actually hit every living person in the United States. There's always at least a handful of people that fail to answer their census. The government actually makes a big deal out of it too. They mail it out to you, and if they don't get it back to you, then they send somebody to your door. It actually is a crime not to respond to the census, just so you know. A sample. A sample is a smaller group selected from the population. Why would we select a sample? Why would we not just gather information from the population? Well, the two most important ones that always go together, time and money. You know, let's say we're in a city of 10,000 people. If 7,000 of them are registered voters trying to survey, or actually it'd be a census, we're trying to contact every one of them, that would take a lot of time and a lot of money. This one sounds just like time, but it's a little bit different. Time sensitivity. What this means, to be a completely valid, perfect statistical study, you would pick the people that you are going to ask the questions, and then you would ask the questions of all of them at the exact same time. So you'd either get all of them into the same room and ask them all at once, or you'd have a whole bunch of people that call each of them and ask at exactly the same time. You know, let's say you select your group of people that you're going to survey, and you decide you're going to spread it out over 4 days. So you call, 50 people, you're going to do 200 people, you call 50 people a day for each of those 4 days. So you call 50 people on Monday, get their response, 50 people on Tuesday, get their response. Tuesday night's the debate for the school board election. Well, somebody could say something really stupid or really smart and change the mind. So that the next day when you go to survey people, you're not surveying them under the same conditions anymore. It's changed the conditions that you're working under. And many of the people that you surveyed on Monday and Tuesday may have changed who they would have voted for now. So you have to be able to get it done in a short enough period of time that the conditions haven't been significantly altered. Fourth reason is identifying the population. Like we said in this school board example, some of those people don't know if they're in the population yet because they're not sure if they're even going to vote. So if they don't know whether they're going to vote, we don't know whether they're part of the population. Now, for you guys, this is a very important one. For many other people, it's not so important. Destructive testing is another possible reason. Again, not every test is destructive, but in quality control, oftentimes it is. You might have a part that needs to hold a certain amount of force, so you'll take a part off the line, you'll put it in a machine that applies force to it. Well, you want to go into the safety margin. Normally what they do is rather than applying force to that part and see if it holds and throwing it back in the bin, they'll actually apply force to it until it breaks. And they'll see what amount of force it held. Let's say it needs to be able to handle 2,300 pounds. You put it in a machine and it snaps at 3,900. That's telling us if it snapped at 3,900 pounds, it's probably good up to 2,300. There's a safety margin there. It all depends on your material. I can't just throw it a flat percentage or anything like that. It has to do with the characteristic curves of your material. Certain material, it's called an elastic zone, where it stretches a given amount for every pound of force you add to it. But then there's a curve, and it's at that curve we want to stay well away from that curve in that graph, which if this were a material science class, I'd go into that more. But you want to stay well away from that curved region called the plastic zone. And so you establish the ultimate strength, and depending on the material, the ultimate strength is where it breaks. Depending on the material, the safety margin, the end of that plastic, the plastic zone, or not the plastic, the elastic zone, which is where you want to work down here, is a certain percentage of that ultimate strength. So if it snaps at 3,900 pounds, let's say you're at a 60% ultimate strength. Well, 2,300 pounds is more than 60% of 3,900, so you're safe. Does that make sense? Now, that's for manufacturing. Destructive testing actually can take place in other forms where the questions you ask significantly alter the population. You may have experienced it or seen it happen where if you ask enough shady questions about someone, it starts to change people's opinion about them. You probably experience it right now on the national level. You can only ask and investigate so much before people start thinking somebody's got something to hide. Whether they do or not, asking the questions can sometimes cause things. That is actually kind of falls in that category of destructive testing, where performing the test drastically changes the population. Now you can see why with destructive testing, why you would not want to test every part. Because if you tested every part, they'd all be broken, nothing left to sell, right? So that population or that sample is very important. But to be useful, it has to be what we call a representative sample. We talked about a parameter describing a population. A statistic is describing, it's the answer to that question. But it's describing the sample. So back to that school board election, let's say we called there 200 people and we came to the conclusion 60% of those people that responded to our survey said they were going to vote for candidate A. That's a statistic. That's talking about our sample. After the election, 57% voted for candidate A. That's the parameter. So a survey is that process of gathering information from that sample. So the census gathered information from the whole population, the survey from a sample. Well, back to this idea of a representative sample. To be a representative sample, the sample statistics have to be approximately equal to the population parameters. They're not going to be perfect. The difference between them is something called sampling error. So the main purpose in statistical testing is to minimize that sampling error. Sampling error can come from two things. It can come from poor methodology if you were talking about quality control. That's what's called assignable cause variation. Or it can come from random effects. And that would be, if you're talking about quality control, that's something called common cause variation. Common cause variation cannot be controlled. There is going to be randomness in everything that happens. It is the assignable cause variation that we want to try to limit. So we want to make sure our practices, our technique is as valid as possible in order to try to limit that assignable cause variation. Let's talk just a little bit about that common cause, the random effects. Let's say you're testing parts off that line. You're testing those parts to see if they hold the strength, the force that they need to. So once every 20 minutes, you go out and you grab a part coming off the line, you go in and you run it through your test. There is a small chance that you might just be grabbing parts off the line that are really strong, and the rest of the parts on the line are too weak and aren't going to hold the force. Does that make sense? You know, because what's going to happen is as those parts are produced, some are going to be weaker, some are going to be stronger. Most of them are going to be right in the middle, but there's a chance that you might be just, let's make it look like a curve like this. Most of the parts are going to be right here in the middle, but there are going to be a few that are weak and a few that are really strong. And it might just be that somehow you're getting lucky and you're grabbing parts that are up in here. And they test out and they're perfectly strong. Where in reality, most of the parts are down here and they may not quite be strong enough. Now that's very unlikely that you're going to do that over and over and over again. So we're trying to limit the possibility of that. And to limit that possibility, usually we're trying to limit that possibility depending on what type of, we're either to under 5% or under 0.3%, depending on which practice we're trying to use. The old practice was 5%, trying to limit the chances of a sample altering your results to 5%. You guys heard of Six Sigma training in industry? It's a big group that goes around and does quality control training in a lot of manufacturing sets. They shoot for 0.3%, but they try to limit it to. And all it is just a different standard and some different techniques for trying to limit it. We'll see where those percents fall into place here in the next couple of days. So how do we try to limit the poor methodology? Well, the best way to do that is to take that good sample, that representative sample. The problem is we never know whether our sample is representative. We don't know what the population parameters are, so we can't really compare our sample to it. I mean, the whole purpose of taking the sample is to try to predict. We're trying to use that sample statistic, those sample statistics, to predict the population parameters. So if we knew the population parameters, we wouldn't need to take a sample in the first place. So how do we limit that? Well, the first thing is sample size. If we go out on that assembly line and grab one part an hour and test it, we've tested 8 parts in an 8-hour shift. Depending on how many parts are produced, that may or may not be adequate. If you're producing only 50 parts an hour, if it's a more complex process, testing 1 an hour might be adequate. That's testing 1 out of 50. If you're producing 2,000 parts in an hour, testing 1 part an hour, probably not anywhere near enough. So you need to test enough that you're getting an adequate picture of it, but not too many that you're destroying all your profit. So in manufacturing especially, that becomes a balance. Usually, bigger equals better statistically. The larger your sample is, the more likely it is to be more like your population. Go back to that school board example. It would be really easy to randomly select 5 people and have all 5 of them be in favor of candidate A. It would be really tough to select 100 people Again, randomly, you're not intentionally looking for them, but randomly selecting 100 people and having all 100 of them favor the same candidate. So the bigger the sample is, the more likely you are to get some real variation in it. Now, sample size is one of those things where different textbooks kind of vary on. Statistics is not a cut and dried black and white science. There are different schools of thought on stuff, and sample size is one of those areas where it differs from one school of thought to another. Some say sample size of at least 30 is vital. Others say you can be smaller than 30, but if you're smaller than 30, you've got to meet certain qualifications. Others give things like it has to be at least 5% of the population, between 5 and 10% of the population. We're not going to get into things like that. We're not actually going to get time to perform any samples, but just feel that there are different standards out there for sample size. The big one is sample selection. Let's say we want to select a group of n items. N is the abbreviation we use for the sample size, the number of items in a sample. So let's say n equals, we're going to choose 20 parts during an 8-hour shift. So n would equal 20. Does that make sense? To select the sample, it is very important that sample is random. So what is our technical definition of random? Random means every item in the population has equal chance of being selected. This is a mistake that's commonly made in manufacturing. They start up the machines, especially if it's a place that shuts down at night, only runs 1 or 2 shifts. They start up the machines at the beginning of the shift, and usually quality control will say, we're going to ignore the first few parts. We'll let them get up and running before we start testing. Well, what would be the possible justifications of not testing any of the first parts off the line? So what would that possibly mean about those parts? They're going to be off. So if that's your justification for not testing them, you should be throwing them out. And if you're throwing them out, they're not part of the population, right? Because they're not parts you're going to try to sell to a customer. We don't care about parts of scrap. We care about the parts we're going to try to sell to a customer. So they wouldn't be a part of the population. But there are a lot of companies that start up those machines, they run the first 100 parts, they don't bother to throw them out. Technically, if that's the case where your machines need time to warm up to get up to specs, every part during that warm-up period should be set aside and either scrapped immediately or set aside for when there's time, you test them individually to decide whether they go into the batch or not. So that's a whole separate side of testing, is that warm-up period. Now, normally if it's doing destructive testing, you'd probably start out with the first part and test it. And then you'd probably test every 10 or so, or every 20, depending on how many parts are in that warm-up period, until you hit one that meets specs. Then you'd back up. And then the ones that came after that point, you'd throw into the batch as possible viable parts. Now, there's something a little bit stronger than random sampling, and it's called a simple random sample. A simple random sample means every sample of size n has equal chance of being selected. Now, simple random samples do not occur very often in manufacturing because how often would they grab 2 parts in a row off the line and test? Not very often, right? They kind of want to spread them out so they're getting a better picture. But it's possible to have a sample if you're randomly selecting. It would be possible to have a sample where you did take two parts in a row. So manufacturing often is not a simple random sample. It is random, but not a simple random. Let's take a look at the differences. I'm going to look at some potential sample types, and then we'll classify them as random or simple random or neither. We're talking about something called the convenience sample. If I asked you to conduct a survey to determine if students at WITC are satisfied with their education, don't answer that question, by the way. I'm sometimes nervous to know. If you walked out of here, and I told you you need to survey at least 20 people. If you walked out of here and took the next 20 people you ran into in the hallway and asked them if they're satisfied, that's a convenience sample. Is that random? Why is it, what kind of, you said? Okay, well, let's look at this. Does every student at WITC have an equal chance of being in that sample? No, so it is not random. Students who don't have Monday classes could not possibly in that sample. Let's say you don't go down to the other end of the buildings. Only students that are at this end of the building have a chance to be in that sample. Students at other campuses don't have a chance to be in that sample. So it is a convenience sample. You take what's easy to you. Now, the example I gave you is kind of extreme, but there's other examples that are a little more extreme. Like I've seen political surveys done where they'll actually go outside one candidate rally and they'll survey people as they exit. And they'll come up with, hey, 82% of people favor this concept. Well, yeah, because you took the candidate who's pushing that concept and you waited outside their rally. Or another common one is to wait outside a church and survey people as they leave church. You know, usually the religious views and certain political views go together. So there's all sorts of different ways that you can conveniently select data that gives you a very poor sample. So that is not even random. Let's look at something called a stratified sample. So let's look at the WITC example here again. So the first thing you're going to do is you're going to divide the population into groups. Well, we're going to say WITC has 4 campuses. That's our 4 groups. And then you select from each group proportionally. Everybody has an equal chance. So let's say that there are, I'm just going to list the campuses here. Rice Lake, New Richmond, Superior, and Ashland. And let's say that Rice Lake has 400 full-time students, New Richmond has 600, Superior 250, and Ashland 100. That is a total of 1,350 students, right? Well, let's say that you decide what you're going to do is you're going to survey 40 from Rice Lake, 60 from New Richmond, 25 from Superior, 10 from Ashland. That's proportional. 10% of each population is your sample size, or of each subgroup. It's still all one population. So what you've done is you've guaranteed you had equal representation from every campus. This is random. Everybody does have equal chance. Is it simple random? Well, no, because your sample size here is 135 people. It is technically possible, if you did a simple random sampling, it's technically possible still to select all of your students from one campus. Except for Ashland, there's not enough students there to fill out the whole sample. But you know what I'm saying? It is technically possible to randomly select students and get them all from one campus, even though you weren't trying to. So it is random, but it is not simple random. This does happen in manufacturing a lot, stratified sample, where you divide up different parts of the day, and you want to make sure you get a certain number of test samples from different times of the day, or maybe different operators on the same machine if they rotate during lunch and breaks and stuff like that. So you want to make sure that you select from each of those sections. Let's talk about a systematic sample. A systematic sample is a randomly selected starting point. And then the system goes from there. Let's say in manufacturing you have a machine that produces 100 parts per hour. You are asked, you need to test 2% of parts. So that means 1 out of every 50, right? So what you do is at the beginning of the day, you randomly select a number 1 through 50. Let's say that today you chose the number 14. So then you would take the 14th part off the line, the 64th part, the 114th, 164th, 214th, every 50th part after that. Does every part have an equal chance of being selected? Yeah, because you chose 1 through 50. So it is random. Is it simple random? No. Again, you cannot choose 2 parts in a row. So it's not simple random. This is probably the most common one used in manufacturing, by the way, is a systematic sample. They randomly choose a starting point. Now again, you do have to determine whether your machines have a warm-up period, and you have to exclude that warm-up period before you get your starting point. There's something called a cluster sample. Similar to the stratified sample, you divide your population into groups again. But then rather than selecting some from each group, you select whole groups. This gets done a lot at WITC. Your groups are probably the classes you are in. You guys are a group. And then when we do our student satisfaction surveys, they actually select course numbers, and they go into that classroom and they survey every student in that classroom. So they don't just randomly select students and come out and test you one at a time, because that wouldn't make sense. If they randomly selected students, well, there might be only one of you in here that gets surveyed. So they come in here and survey one, then you go to the next room and survey 1 or 2 people, and they'd have to jump all over the school to survey people. By selecting whole classes, they can survey the whole class and get a bunch of data all at once. This is especially useful for like door-to-door surveys. I don't know why I made my street so wide, but you guys get the picture. Let's say we've got a city and we need to go, or an area of the city, and we want to go door to door and ask. Well, if I randomly selected people, I might have, there and there and there, and people scattered all over that I have to survey. I'd have to travel all over the place and knock on those doors. If I do a cluster sample, I would say, hey, I'm going to do this whole block, this whole block, this whole block, and this whole block. So that way I can go park my car on the corner and walk around the whole block and knock on doors. More economic. A cluster sample, if done correctly, is still random. I'm going to caution there. It's definitely not simply random. Nope, I'll explain in a second. I have to caution there about the randomness. You have to be very careful that the groups are approximately the same size. So like the classes, choosing classes to do the student satisfaction survey, technically that's not random because every class is a different size. So you got to be really careful how to do that. Because when the classes are different sizes, the groups are different sizes, well, if you select one group over another, now it changes the probabilities of others being selected. Because if you choose a small group, well, then you're going to have to choose more groups. It's a tricky. It is not simply random because it's not possible to have a sample that only has one person from a block. So it would be possible in a simple random sample, it would be possible to have one person from each of the groups or two people from each group. In a cluster sample, you have to have the whole group. So if one person in the group is in the sample, everybody else has to be. So it's not simple random. So let's get to it. What would make it simple random? Simple random sample in statistics is held up as the best. Not always practical. Back to that student, are they satisfied with their degree? You would assign everybody a number or write down their names. You'd put them all in a hat and you'd draw them out. Let's just use the student ID number of all the students. You'd print off all their student ID numbers, cut them up into little slips, throw them in a hat, and let's say you're going to do let's say you're going to survey 100 people, 100 students. You draw 100 of them out. There is no limit. I mean, every student has an equal chance of being chosen, and every possible group has an equal chance of being chosen. Like I say, it's highly unlikely that you're going to select everybody from one campus, but it's possible. So this is not only random, it is also simple random. It is, yes. And you have to be careful how that's done. If you draw them out and then you put the name back in, it's not. But if you draw them out and just set them aside and keep going, it's simple random. Yeah. Probably it all depends on the specified rules we're going into. Any questions? So I want to talk a little bit about that question being asked. We ask a question in statistics. The answer to that question is a random variable. Who do you plan to vote for in the next election? You'd answer candidate A or candidate B. That's the random variables, that answer. For you guys, maybe you're testing the size of a part or size of a piece of a part. What is the diameter of this piece? You'd measure it, and that diameter would be the answer to your question. That's a random variable. Random variables can take on one of two main forms: categorical, often called qualitative. Qualitative means we're measuring a quality of the part. The school board question is a categorical variable. What candidate, candidate A or candidate B, answering the question puts you in a category. That measures a quality about you. Categorical data can hit a couple of different types. It can be ordinal or nominal. I'll start out nominal or ordinal. Nominal means by name only. Which candidate are you going to vote for, A or B? Whichever one you pick puts you in a category. That's a nominal category. Ordinal, if I ask you what was your letter grade in this class, well, A, B, C, or D, that puts you, it's still a category, puts you in a category, but it's ordinal because an A would be better than a B. There is an order, a natural order to rank them in. Or if you go to a restaurant and you just survey, the size of a soda ordered with the meals. Well, small, medium, and large can be put in order. So even though your answer is a category, you can put them in a logical order. The other side of that is numerical or quantitative. So your answer is a number of some sort. So what was your points did you earn in the class? What was your percent in the class? That would be a numerical data. Your letter grade would be categorical. What's your height? That's numerical. How long did it take you to complete this task? That's numerical. Any yes or no question is categorical because that puts you in that category, yes or no. Now, numerical data gets divided into two subcategories. There's discrete and continuous. Discrete simply means can be counted. How many cars do you own? You can count them. How many classes do you have? You can count them. How many children do you have? You can count them. Continuous is generally measured. How long did it take you to complete that part? That's continuous. You're measuring your time. Now, ones that fall into a gray area. Money. People say, well, money is decimal, but you can technically, if you limit money to the penny, you can technically count money. Money quite often gets classified as discrete. Usually it's classified as discrete. Now, continuous, that doesn't mean continuous isn't going to be rounded at a certain point, but your rounding in a continuous variable is only limited by your measuring device. Let's say you're using a micrometer that can only go to the 10,000th of an inch. You're going to round the nearest 10,000th of an inch, but you only did that because that's the limits of your device. Theoretically, you could round to as small of a unit as you wanted to. One of the technical definitions of continuous is no matter how close two things are, you can always find something in between them. So if you think of a person's height, no two people are exactly the same height if you measure down to a small enough unit. And no matter how close two people are, you can always find somebody in between. It's possible to find somebody in between them if you measure down to a small. What's that? Well, they're still there. So it's always possible to find something, theoretically possible to find something in between. Okay, that's probably a good place to end the vocabulary. There is no homework today. Tomorrow we'll start talking about organizing these different types of data into tables and graphs, and that's where we really start the meat and potatoes of it.